Okay, so our job now is to solve the conformal killing equation. And we're going to solve it for various values of d. And in fact, it turns out that d is equal to 1, d is equal to 2, and d is greater than 2 are all very different. So they are all very different. So we're going to have to deal with these cases separately. I'm not going to talk much about d is equal to 1. For me, at least, that's the least interesting case. But what I am going to do is I'm going to start off by discussing d is equal to 2. After we've done d is equal to 2, we'll go to d greater than 2. Actually, d greater than 2 is our main interest in this course, but we'll start off with a discussion of d is equal to 2. And at d is equal to 2, we will discuss this first in Euclidean space. So we can always make a choice. Are we working in Minkowski space or Euclidean space? So we'll start off in Euclidean space, and we'll just use the normal flat metric of Cartesian coordinates. So I don't know, we could say ds squared is equal to dx1 squared plus dx2 squared. And now we can freely raise and lower indices because we're in Euclidean space. So in d is equal to 2, what is the equation that we're studying? Well, we've got d beta zeta alpha plus d alpha zeta beta is equal to, and now the 2 and the d cancel. Then we've got d dot zeta, and we've got the metric is just delta alpha beta, the usual Kronecker delta. Okay, so let's plug in alpha is equal to beta is equal to 1. We're just going to plug these index values in. So we'll get 2d1 zeta 1, because both terms on the left-hand side are equal. So I just add them to get 2. Then d dot zeta 1 will be d1 zeta 1 plus d2 zeta 2. And this is multiplied by delta 1, 1, which is just 1. So bringing everything over to one side, we learn that d1 zeta 1 minus d2 zeta 2 is equal to 0. So this is the first equation that we get. You get the same equation, so you should check this. You get exactly the same equation if you plug in alpha is equal to b is equal to 2. Okay, now we can set alpha is equal to 1 and beta is equal to 2. So, well, if we plug that in, we're going to get d1 zeta 2 plus d2 zeta 1 is equal to another Kronecker delta, delta 1, 2 is equal to 0. So that's the equation that we get. And you can again check that we get the same equation if we set alpha is equal to 2 and beta is equal to 1. So the content of the conformal killing equation in 2 dimensions in Euclidean space are these 2 boxed equations. So what is the meaning of these 2 boxed equations? So that's what we're going to discuss now. And these 2 boxed equations are nothing but the Cauchy-Riemann equations. Okay, so the Cauchy-Riemann equations are very famous equations in mathematical physics. There are lots of things that you should know about them. I'm just going to review the bare essentials of what you'll need so that you've got a good idea of what's going on here. And these are the facts that we use again and again. So to motivate what's coming next, I want to ask a very simple question. So let's imagine that I have got some function, f, which I'm plotting over here, and x, and my function does something. And what I'm interested in doing, I'm interested in calculating the derivative of my function. So you'll all know this, but let's just put it down because it is setting the right stage for us. So to calculate the derivative, we pick 2 points, f of x plus h and the f of x, and the derivative of f with respect to x is given by, you take f evaluated at x plus h, and you subtract from that f evaluated at x, and then you divide by h. And then to get the derivative, you take the limit that h goes to 0. And this will give you that the derivative is the slope of the line and all of the things that you're really used to. So that's something that should be completely trivial, something that you know very well. Now, let's take a look at the complex plane. So if I think about the complex plane is two-dimensional. So let me draw the 2 dimensions here of the complex plane. We call this horizontal axis x as usual. We call the vertical axis y as usual. And if we pick a point on this plane, we label that point by a single complex number. And that complex number z, it has a real part, which is x, and an imaginary part, which is y. So because there are real and imaginary parts, to plot out all of the complex numbers, we need a plane, as opposed to the real numbers where we only needed a line. And then if we want to calculate the derivative, well, the f dz is defined in a very similar way. We take the f of z plus, I'm going to call it delta z, minus the f of z, and then we would divide by delta z. And we get this derivative when we take the limit that delta z goes to 0. And that would then give us the derivative. The reason why we are looking at this formula for the derivative is that we are now going to argue that the Cauchy-Riemann equations are the conditions for a function to be complex differentiable.